Welcome to this video. We are discussing about probability, and we learned that probability is about counting, right? So here in this particular session, we want to expand on the discussion on counting, to systematically count regularly defined, that means well-defined, very infrequently encountered situations, to count those situations very quickly and accurately. So already the formulas have been developed, and it's very easy to understand and apply, and it becomes a bit of a weird situation if we refuse to learn or don't learn these formulas, right? So what I want to talk about, I shouldn't be using equal, is n factorial. So that's called the factorial. You might find this in your calculator as well, right? And slightly more scientific calculator might also have NPR, and you call this the permutation function. And finally, we also have NCR, the combination function. Again, in more scientific calculators, you could also find this symbol somewhere in the keys there, right? So these are very useful formulas. That's it, just 3 of them, and that's good enough. Okay, let's begin with consider a stack of poker cards. One stack, just one stack, right, of 52 standard poker cards. We can also analyze dice, but dice is rather easy enough unless you have multiple dice. And if you have multiple dice, might as well just think about cards, right? So 52 poker cards. And we're using poker cards not because we have casino in Singapore, right? But everybody, has seen poker cards before, even if you don't play. And if you're not sure, you can always buy a stack of poker cards and analyze them if you like, right? So it's a very tangible physical form of a tool for us to touch our hands on and literally count them if you like. So let's begin by asking, right, if we have 3 cards, for simplicity, we just draw, is that spade? Right. So Jack, Queen, and King. If we have 3 cards, right, suppose we have 3 cards. It can be 3 students or 3 tour guides or 3 supervisors or 3 projects. Just use your imagination. So the idea of using cards is just that it's very commonly understood, right? Rather than saying, let's have 3 teapots. So 3 cards, and I just standardized to spade. And so it's Jack, Queen, and King, very uniquely defined. 1 card only, each having 1 card only in the stack of cards, right? So we throw away the rest. Just look at these 3 cards, and we ask the question: how many ways are there to order them, where the left to right sequence matters? Okay, so one important thing is that you, as the student trying to answer the test question, right? Does order matter? This is the most important question you must ask yourself, because sometimes the test question doesn't put this in explicit form. By right, it should, but sometimes they make it harder or expect you to be able to understand common sense, right? Or you should be able to know that the order matters or the order doesn't matter, right? Example, how many ways are there to form a debate team, student debate team consisting of 3 students per team? Well, you should know, right? Common sense, that order doesn't matter, right? But wait, I have been in the debate team, says one of you, right? And the order matters, because the last speaker tends to be, having better flair at presentation and whatnot. Yeah, you are right. But did the question say how many ways are there to arrange the fixed 3 students? Right, don't have, right? Here we have fixed 3 students. And now we are asking the question, how many ways are there to order them, to form a team, such that each student is seated with 2 other students in different manners. So here, student Jack will speak first, then Queen, then student King. But we can have other combinations, right? So if order matters, then it will be like this, and then we exhausted every permutation order starting with J. Then we have Queen, let's say. Then we have J, K, then Queen, K, J. Yeah, you can easily follow, right? And it's okay, we can list them all out because I have already calculated it's going to be 6. Because you have also seen that we have exhausted all the way that we can never think of to permute them, to reorder, to resort the students and present the names in that manner, right? So like speaker 1, speaker 2, speaker 3. Right now, yeah. So if the test question says how many ways are there to form a debate team with 3 students, then where of course the last speaker needs to be the strongest speaker, and that part is to hint to those of you who haven't encountered such a team formation before, that the order matters. So there's a hint there, right? So these are a little bit tougher question where they don't tell you explicitly this answer to this question, because the core of knowing how to count is, does order matter? Okay, so how many ways are there to form a debate team for these 3 students? Order matters, then 6. Order doesn't matter, how many? 1. Because that's the combination of cards, combination of the group of students, the collection of students, right? So we use these words, group, collection. Yeah, usually group, there's a slight gray area, but tends to be more frequently associated with order doesn't matter. So a group of 3 students. So if order doesn't matter, I already have the group, 1 way, that's it. But order matters, then we see that it is like this, right? So it is 6 factorial. So here we have 3 cards. So total number of permutations. That means arrangements where order matters. That's one short word for arrangements where order matters. That's why this will be our weapon to use if the question cares about the order. So we will use permutation. So this is equal to 3 factorial. What is 3 factorial? That means basically just equal to 3 times 2 times 1. Finish. So of course, 1 factorial is 1 and 0 factorial is 1, not 0. Huh? Okay, but so 0 factorial is okay. You can divide by 0 factorial, no problem, because it's just dividing by 1. Okay, so 3 factorial. Now, how to think about it? How do I know it's 3 factorial, right? First of all, I look for hints and signs that order matters, yes, okay? And then what, right? So let's think of it as, let's just think of the 3 cards, J, Q, K, as a collection. So they are stored in a NTUC bag, right? So they're stored in a bag in no particular sequence. They're all jumbled up. And we have 3 parking lots. Is that okay? All right, so 3 parking lots. So now we ask the questions, right? If we randomly pick our hands inside and then pick out a card and put here, right? And of course, it's dwindling. If we pick out J, then we only left with Q and K. If we pick out K, then we are left with Q, right? So how many ways are there to form unique letterings? That's the same question. That's the same question. So how many ways are there to form unique letterings? By drawing the letters from this NTUC bag and then placing it in sequence. Okay. So I would randomly pick J, then I'll pick Q and K. That's one way. Then I'll randomly pick J. It could also be K, Q. It could also be Q first, then J, then K. You see that? So we start to list out in the same manner. And then the question is this. If we now have 3 and we choose 1, so if we have 3 and we choose 1, that's basically first we have 3 choose 1. 1 card. 3 cards, right? At first we have 3 cards, then we choose 1. So this is the combination. Another way to think about it is N choose R. This is N permute R. Permute, remember, the word is a little bit maybe stranger to us, but just saying N permute R, that means we want to arrange R cards out of N cards in ways that are unique. We'll come to that in a while, right? This one is N permutations. This one is what we have just done. How many ways are there to arrange them such that the order matters? So N permutations, we have done that. And what we are doing now here is also in a way, using N choose R. So what we are doing is 3 choose 1. So it can be anyone, but we know that we are down to 2 cards, right? After choosing 1, it can be J, it can be Q, right? So once we put this here, we have 3 choose 1. And then we go about knowing that we have 2 cards left. So 2 choose 1. So then we put it here. It doesn't matter whether we pick Q or K or J, it doesn't matter, right? So this is 2 choose 1. And finally, we know that the last one, we only have 1 card. The easy way for most of you would say, well, that's it, there's only 1 way. But you're reasoning, and we don't want that manual, tailored, customized reasoning all the time. We want a very systematic way. All right, we're having 1 card, we need to choose 1, so 1 choose 1. So it's like no difference. It's just like the 3 case. It's the 1 case, even though it's so simple, it's just like the 3 case. But let's flip it. The 3 card case is just as simple as the 1 card case. Or if we have 300 cards here to choose from, the 300 card case is the same, or the simple way to think of it, as the 1 card case. So here is 1 choose 1. Okay, so how do we go about calculating 1 choose 1? Well, we just use R, right? There's a function in R to calculate 1 choose 1. Or we can just simply use the factorial function in R. R has a factorial function. So in R, we can use this easily. For NCR, that's just equal to, n factorial over R factorial, n minus R factorial. And for permutation, it is, by definition, n factorial over n minus R factorial. You don't have to memorize these because all these formulas are done in R easily, right? So factorial is just factorial. So factorial is just n times n minus 1 times n minus 2 times all the way down to 2 times 1, and don't times 0, right? Okay, so we don't need to memorize this or do this manually, and that's the whole point of using R to calculate this rapidly. But the question is, more importantly, your understanding. When do I use it? How do I know I have to use it, right? So I'm trying to analyze it, take it apart to show you the science telling you exactly what to do, or to rethink the problem, right? So here, suppose we say, wow, it's so difficult to list out everything, right? I'm not sure. I list out until here, and I couldn't see whether, I wouldn't know whether I have missed out another one way or two ways, right? Yeah. So how do I go about it? Well, like I say, rethink the problem. So I have 3 cards put in a bag. How many ways to choose? To put in a parking lot that displays the first card, right? Order matters, like this. So now that we have this, we simply times them together, and that's it. So we have 3 choose 1, right? 3 choose 1 is 3 factorial over 1 factorial, that's 1, right? So 3 factorial over 1 factorial, or 3 minus 1 factorial, times 2 factorial over 1 factorial, 2 minus 1 factorial, times 1 factorial, 1 factorial, 1 minus 1. That's not infinity, that's 0 factorial. And you can see this is basically 3 factorials, 3 times 2 times 1. This is 2 factorial. So there's 3 times 2 times 1. You can just work it out. Answer is still the same, 6. And if you do this, it is also 6. All right, it just goes to show that different ways of thinking about the counting still works, right? But this is about fixed number of cards here, all right? And I'm trying to arrange them, and I have to use all of the 3 cards. That's factorial. No way to run. Must use all. I give you 3 students, 3 cards. You must arrange them all. So that's factorial. Because another way to think about it is n factorial is basically equal to n permute n. Because if you put the n inside R, n minus n is 0. So 0 factorial becomes 1, right? So that basically means npn is just n factorial. That's very illuminating because I'm trying to have n cards and I need to permute all of the n cards. See? N factorial, npn is n factorial. So n factorial, we know I give you 3 students, you go to permute all the 3. Remember what's permute? Arrange them where the order matters, right? So you need to permute all 3. I give you 3, you permute all 3. That's npn. I give you n, you permute all n. That's n factorial. But permutation gives us the freedom to permute lesser than n. Lesser than n. Now that's interesting. Now let's say we have, let's consider, right? Now consider 52 cards, right? Consider 52 cards, all 52 cards, fresh cards. Now the whole stack, right? Okay. Well, how many ways are there to permute 3 cards? Or another way to say it is like, how many ways are there to place 3 cards on table where order matters? That's a different way of interpreting this word permute. If the question says permute, it's very friendly. It's telling you order matters. Where it's less friendly is how many ways are there to place 3 cards on the table. Then the order matters part, they use something else to talk about. Maybe they say from left to right, from top to bottom, from closest to the dealer to furthest from the dealer. That means the sequence matters, right? So they are telling you hints and ways to say that. Must answer this question first, right? Because if order doesn't matter, we use NCR. So same thing. Consider 52 cards. How many ways are there to permute 3 cards? To choose 3 cards. Choose is typically a test question hint that says don't care about order. To choose or to form a collection of 3 cards. To group 3 cards. You know, basically the wordings are grouping, choosing, collection, or bagging, like put in NTUC bag that I was saying. Don't, I mean, that means those, in those situations, order doesn't matter. Otherwise, you've got to be careful. Or it may be that it matters, maybe that it doesn't matter. So analyze the words. So here, clearly order matters. So what we want is, so the answer is number of ways, number of ways. So I want to like draw a line here. Okay. Number of ways is clearly 52p3. Can you see the numbers, how they come in? My like reservoir is 52 cards. I need to pick 3, you know. It can be ace, j, queen, jack, 2, 7 of different color and what do you call that? The icon, right? So you can then basically don't care about those and use 52 because we will consider all 52 cards. We will pick 3 cards and treat each card as unique, and that's it. So from here on, you can just directly port into R or your calculator, right? So as to de-emphasize the complexity here. But right now, I don't have an easy reach to my calculator, so I will just also as a matter of illustration show you how I substitute them in -3 here, right? Yeah, okay. So that is not too scary to calculate because denominator is going to evaluate to 49. Yeah, and 49 factorial means 49 times 48 times 47. So this is 52, 51, 50, then 49, 48, 47, right? So the whole 49 downwards, and here all the 49 downwards, they're going to cancel out. So it's simply just starting from 52, 51, then stop at 50 because the 49 is the denominator and the 49 in the numerator will cancel off from the 49 in the denominator downwards, 48, 47. So that's just to, you know, manually think through. But if you use our calculator, totally outsource that to calculator. So then you calculate, and that will be the number of ways. But just for the satisfaction of knowing the number, 132,600. Okay, so that would be the ways to put them on the table. And of course, if order doesn't matter, right, then how many ways? Many ways to pick 3 cards. That means don't care about the order. That's typically the way we play games in poker games, right? You just deal the cards to the player, and doesn't matter whether your combination of cards come at the start or at the end, right? Of course, it will affect the stakes that are raised in each round, but then as your final showdown, the 5 cards typically doesn't matter whether they come at first or at the end. So that's more like a combination. How many ways to pick 3 cards? That's all, right? So order doesn't matter. So number of ways. So order doesn't matter. Order, let's put that down since we're learning. Order does not matter. So number of ways, 52, C3, right? C3. And that's just 52P3, yeah, divided by, so that's NPR, whatever you have there, divided by R factorial. Yeah, because if we bracket this, then that's NPR. So you just divide by R factorial. So we can just conveniently use that on top to say that it's 1 divided by 3 factorial. So it's 132,600 over 6. And the answer is 22100. Did you get this? Okay, so you can see that if the order doesn't matter, then it's just your hand, right? Your handful of cards, the 3 cards on your hand. You can shuffle them, right? Put the last one on top one at the last and whatnot. A lot of combinations will have been eliminated, right? So because it's the same hand, we call it a hand of cards, right? So doesn't matter whether it's JQK or QJK or doesn't matter, right? So that's just one hand of card, and number of different hands, right? Different ways we call it is a lot lesser than if we care about, oh no, the king was received first, but your hand, the king was received on the 3rd round, so it's different from mine, or therefore it's more expensive, or therefore I pay you lesser, or whatnot. Then that's a different game altogether. And of course, harder, a lot less probability to get exactly same sequence. So a lot of the probability comes from this, whether it's in the denominator or the numerator, right? So we need to count very, very quickly and accurately. Okay. So suppose we say, let's just have, so we have talked about the permutation and combination. A lot of times we're going to use combinations to systematically build up, all right, build up the cards or the required assembly, like forming a team of debating students. Like we need 3 students. We have a class of 52 students that are 52, right? 52 cards, 52 students in the class. We need to form a debate team of 3 students. Debate team first. I didn't care about who is going to speak first or who is going to speak last. How many ways are there? Well, that's just 52 students picking 3 as a group. Doesn't matter Tom is picked first or picked last as the 3-member team, correct? So that's order doesn't matter. 52C3. Right. So this has a lot of applications. So we'll look at this one. Right? And even in cases where it's permutation, you can also first work out the combinations, then times back the permutation within the chosen grouping, right? Then you will get the permutation. So it's also quite, it's reversible in that sense.